If we were to determine, no matter what routing protocol is being used, the level at which the traffic is being generated, we'd have to consider the total number of requests that are being made and the total number of replies and the overall file size. For the sake of convenience, we can assume that we are considering a non-real-time or an elastic traffic scenario. For that, in this module, we shall understand what are elastic aggregates of traffic, how can we do some kind of traffic engineering to understand the behavior of a network. This will form a very relevant and necessary understanding for developing simulation examples. We'll start with a generalized scenario of client-server communication. Then we'll do demand characterization. The reference for the sake of this module is by Anurag Kumar, Joy Curry in their titled book, Communication Networking, an Analytical Approach. This book is a very useful reference for students who are interested in modeling different aspects, especially the communication aspects of networks. Let's look at the generalized scenario first. Here we see that we have clients which are represented by this dotted rectangle. These clients are connected to the network through a stub router represented as T, which is in turn connected to an ocean of routers. On the other side, we could have a server farm of various web servers, all connected through another stub router denoted as S. We are interested in assessing how much total traffic would be generated from S to T when requests are initiated from T to S on behalf of all the clients. Suppose that a request arrives from one of the clients for downloading a file of size V bytes. Now that a request is made, V bytes have to be transferred from S to T. If we generalize the number of download requests arriving over an interval, if it is NT, then the total file size for this interval is going to be a summation over the whole range I is equal to 1 to NT for V sub I. Now we are interested in determining what are the average number of requests, because then we'll have a better illustration and visualization of exactly how much aggregated traffic is being generated. Suppose that over the interval T, if EV represents the average file size, then the average requests for an aggregate amount form the mathematical relationship. The number of requests represented as NT times the average file size. This determines the average download file represented in bytes. Now we are interested in determining the offered load into the network. When we have looked at both these expressions, that is Vt as a function of Et times Nt, if we divide both sides by T, we see that when Vt is divided by T, it gives us the average rate at which Vt grows. And similarly, the number of requests Nt gives us the average rate at which the download requests arrive. Together, these form the overall load offered to the network, represented as rho, which is a product of lambda, the arrival rate, times the size of an average file. Rho is represented offered load in bytes, and lambda is actually the arrival rate in download requests per second.